Hi, this video is about the problem-solving strategies for circular motion. In the last 2 weeks, we talk about circular motions. Firstly, we talk about all the angle and angular kinematics, the relationship between the angle, angular velocity, angular acceleration, and time. And then starting from Wednesday and today, we talk about the centripetal force and the centripetal accelerations, which is basically the force and the acceleration that is normal, or we say perpendicular, to the velocity. Okay. So now I'm going to just give a brief review on angular kinematics. Then I will solve a problem to talk about some problem-solving strategies, and then I will give another examples on centripetal force and talk about problem-solving strategy for centripetal force. Okay, so let's start from angular kinematics. Angular kinematics is very similar to linear kinematics, except all the xv and accelerations of this kind of variables are replaced with the angle-related physics quantities, such as angle, angular velocity, and angular accelerations. They do have a very close relationship. If you just check the units. The units and the dimensions, you will see that this v is simply r times the omega, and the acceleration is r times alpha. So they do have a very pretty good one-to-one correspondence. But one thing that I would like to mention is that this acceleration, velocity, and x, this linear kinematics which is related to angular kinematics, it's only the tangential part. Because the x will be this arc, the v of course will be the velocity in this direction. Acceleration is also the tangential acceleration. This is not a velocity in this direction. There's no velocity in this direction. And this is not the acceleration in this direction. So here, from this relationship, we can figure out everything tangential related to angular kinematics. And since they have a pretty good one-to-one correspondence, and we also, for a constant angular acceleration motion, we can cook up pretty similar equations and the relationship, just like what we have for linear kinematics. And so you can just use this relationship and to figure out the problems and or so. So here is an example. So this example will show you how to connect the angular kinematics from angular kinematics to linear kinematics. A powerful motorcycle can accelerate from 0 to 30 meters per second in 4.2 seconds. Then what is the angular acceleration of its 0.32 meter radius wheels? So here I have a motorcycle. Let's say this is the motorcycle. And that's the wheel. Okay. So this person is driving this motorcycle. It will accelerate from 0 to 30 meters per second in 4.2 seconds. So from here, we can figure out the linear accelerations. The linear accelerations for the motorcycle will be the change of velocity divided by the change of time. So it will be 30 minus 0 divided by 4.2. So we would have 40 divided by 4.2, which is 30 divided by 4.2, which is 7.1. Okay, so now we have this acceleration. But the question is asking about the angular acceleration. How does this wheel, this angular acceleration for this wheel? So then let's try to make this connection. Since my motorcycle linear acceleration is 7.1, which means each of my wheels need to have a linear acceleration. Now, it gotta be accelerated in this direction for 7.1 to make my motorcycle go like accelerated as fast. So this acceleration, linear acceleration, is also the tangential acceleration on my wheel. Now if I want to find out my angular acceleration, I know that the tangential acceleration are related to my angular accelerations with just a factor of r. So this is 7.1. R is this radius, which is 0.32 with alpha. So the alpha is 7.1 divided by 0.32, that is 22.2 rad per second square. Now with the information of angular accelerations, then we can start to ask, how much angles will it travel after 10 seconds? We can ask about what's the angular velocity of the point of this wheel, what's the angular velocity after 10 seconds or so. Then starting from here, we can ask a lot of kinematics questions. Okay, so this is the solving strategy is you kind of need to read the problems, identify the accelerations, see whether the acceleration is linear, tangential, centripetal, and then when you figure out that, think about the physics, then started to make the connection. The connection between all the angular motions will obey this set of equations. The relation between angular kinematics and linear kinematics will be related by this relationship. Yep, so just play with it and until you feel like you're comfortable with all this change of variables. Okay, so the second part of this video that I want to talk about centripetal force. Centripetal force is, so we just talk about, in the first part, we talk about tangential part. Now we want to talk about centripetal part. Now we know almost everything when they need to change the directions of their motion or velocity. They do need a centripetal acceleration to make the change of the direction of the velocity. And associated with this centripetal acceleration, there's always a centripetal force because we know F equals to ma. But again, F equals to ma, this F is like a net force. It's not a real force, physical force. It's just say, I do need this kind of force to provide these accelerations. And this force has many different kind of sources. If it's a string, a ball attached on a string, and you're swinging it, tension force will be the centripetal force in this case. Or if I have a satellite which is orbiting around the Earth, then the force between them, which is the gravitational force, that force will be the centripetal force in this case. And then, so this is pretty much my F equals to ma. but it's not in the linear kinematics anymore. It will be related to the circular motions. So let's see how do we apply this Newton's law in a circular motion. So let's consider this example. An Olympic ice skater. Skaters are able to spin 9 revolutions per second. And what is the centripetal acceleration of the tip of his nose, assuming it is 0.12 meters radius? So now I draw these pictures to help me think. This is an ice skater, and he or she is spinning. And say let's say it's a he, then he has a huge nose, and which is from the center, it will be 0.12 meters away. That's a tip. So how do we figure out the centripetal accelerations? So we know it will be able to rotate 9 revolutions per second. This information tells me its angular velocity. Okay, now I want to convert it to SI unit. One revolution has like 2 pi in radians, and second is second. So now I have 18 pi radians per second. Okay. And since I want to figure out the acceleration, centripetal acceleration, I know the centripetal acceleration is related to the angular velocity. They have the relationship is A equals to R omega squared. And the R in this case would be 0.12, and the omega in this case will be 18 pi squared. So if we add just some simple algebra, we have the times 18. This is roughly 373.6 meter per second squared. Okay, so this is our answer here. This acceleration is pretty large. It's almost like 40 times greater than the gravitational force, gravitational accelerations. If we want to know how much force that your nose will experience, not your nose, like the ice skater's nose will experience while he is rotating, then we can go ahead and make an assumption. Say if the nose is roughly 10 grams, which is 0.01 kilogram, then the force that your nose, to keep your nose, stick to the face without falling apart, the force you need to provide is the centripetal force, which is MAC, 0.01 times 373.6. So the connection your face needs to provide this amount of force in order to keep your nose to stick to the face without falling out. So this is just a simple example of how to apply F equals to ma for the circular motion. Basically, the problem solving strategy is the same, is that we want to use F equals to ma. The only difference is that the A here is not just simply the acceleration, like the linear kinematics acceleration. It is the centripetal acceleration. So that's related to velocity and R in a very special way. It's either R omega or V squared over R. These two are equivalent. And this force will be this centripetal force. This force comes from different sources. And then so sometimes it will be helpful to draw a free body diagram to actually figure out what kind of physical force will provide the centripetal force that you need. And based on that information, you can go ahead to solve more problems. And so this is just simple examples, and hopefully can provide you some ideas. These problems can be made more complicated if we started to think about a two-dimensional system. For example, the car on a banked curve, and then so that it is rotating. And then in this case, for example, here in this case, we know this car has a normal force from the curb, and it also has a gravitational force. So there are two forces. So it seems like it becomes a two-dimensional problem. And remember that in two-dimensional problem, it will be helpful to separate the x direction and the y direction. So in the x direction, we can see the x direction, we have only Fn, say if this is theta. We have Fn cosine theta, that's the force in x direction. We also, the force in y direction, we have Fn sine theta and minus mg, because that's the gravitational force. So now let's see how to apply this net force in different directions by using this F equals to ma. The net force in x direction will provide the centripetal accelerations that will actually change the direction of the car. So this is the centripetal force. It will equals to mac. While in the y direction, there is no acceleration because the car is not moving in the air, right? So here, E equals to ma, but since there's no acceleration at all, so this is simply 0. So by analyze this problem, I will get two pieces of information, or we say two equations. One tell you that the x component of normal force provides centripetal force to do this circular motion. Another piece of information is telling you that the y component of normal force will cancel out with the gravitational force because it's not moving. But by combining these two informations, you will be able to solve whatever questions or variables that is given. But this is just the generic problem-solving strategies. Okay, I hope this video will be helpful for you, and let me know if there's any specific type of concept or problems that you would like to me to address or to talk about, and I would be happy to either talk about it in the lecture or make a mini video on that example. Okay, thank you.